Did you know that something invisible can slowly disappear but never fully vanish? From medical treatments to ancient fossils, radioactive half-life controls it all. In the next few seconds, I'll explain radioactivity and half-life in the simplest way possible. Let's begin. I'm a nuclear medicine resident, and in this video I will explain what radioactivity, radioactive decay, and half-life are. At the end of the video, I will also give you a simple example of how half-life is used in everyday life. The balance of protons and neutrons in a nucleus determines whether the nucleus is stable or unstable. If there are too many protons or too many neutrons, this balance is disturbed, making the nucleus unstable. Elements with fewer protons, especially those near the top of the periodic table, are stable when they have an equal number of protons and neutrons. For example, carbon-12 is stable because it has 6 protons and 6 neutrons. However, as the number of protons increases, more neutrons are required to keep the nucleus stable. For example, Li-207 has 82 protons and 125 neutrons. Unstable nuclei, meaning nuclei with too many protons or too few neutrons, will disintegrate by emitting radiation. This process is called radioactive decay. Any material that undergoes radioactive decay is considered radioactive, and the amount of radiation it releases is called its radioactivity. Radioactive decay is a spontaneous and random process. This means we cannot predict which individual nucleus will decay next. However, because there are so many nuclei, scientists can use statistics to predict how many will decay over a certain time period. Scientists define half-life as the time it takes for half of the unstable nuclei in a sample to decay. In other words, half-life is the time required for the activity of a radioactive source to drop to half of its original value. Let's look at an example. Iodine-131 is a radioactive isotope commonly used to treat hyperthyroidism. It undergoes beta decay and becomes stable xenon-131. The half-life of iodine-131 is approximately 8 days. This means that if we start with 8 iodine atoms, after 8 days, for atoms will have decayed into xenon, and for atoms will still be radioactive iodine. After another 8 days, half of the remaining iodine will decay, leaving to iodine atoms. The same principle applies if we measure the sample in grams instead of atoms. For example, if we start with 40 grams of iodine-131, after one half-life 8 days, 20 grams will have decayed into xenon and 20 grams will remain radioactive. After another half-life, only 10 grams of iodine will remain, while 30 grams will have decayed. This process continues indefinitely. Although the amount of radioactive material becomes very small, it never reaches zero completely. Half-life is also used in archaeology through a method called carbon dating. Carbon-14 undergoes beta decay to become nitrogen-14. When an organism dies, it stops taking in carbon-14.